In this session, we're going to talk about the end-term test for the series, guys. So far, we have learned, just one technique. It was the sequence of partial sum, and then we took the limit of that sequence to figure out if our series is convergent. There is no other tool we have learned so far. Yes, we have learned the geometric series, and some other series, we looked into it. They were all the examples for the sequence of partial sums. We just applied that technique, okay, to be able to find the convergence of our series. Today we have a real test so that we can check it out if a series is convergent or divergent. But saying the divergency is going to be more correct than saying the convergency after this test. Let me explain what I mean. This is the end-term test in a theorem. The theorem says if a series, you have a series, and then you know that it is a convergent. If a series is convergent, then the limit of the end term of this series, guys, will go 0. Okay, that's the end term test. So here, that's why we say this the end term test. Since it is about the end term. This is my end term. Please be aware of that. Who I say, who is the end term? This is my end term, guys. Okay, you should be careful. What it says, if you know the convergence of your series, then the limit of end term is gonna go 0. As you notice, this theorem, is about the convergency, but we said that at the title, it should be about the divergency. And then also there is another question you may ask, if I know the convergence of the series, why do I need, such a theorem? Yes, you are right. But let's discuss all these, after the proof. Let me show you the proof first, How can I obtain such a result? Proof will be in this way. So we assume that AN is convergent, AN is convergent. If AN is convergent, the only thing I know about the convergence of a series, was the limit of, the partial sum of sequence of partial sum will go a number. So this means, if it is convergent, this means Sn will go L. I'm going to use this information to prove this result. So if the sequence of partial sum is convergent because of my convergence of series, I can use it. What do I mean by Sn? Sn means the first n term sum, So that's why I'm going to add the first n term. Can I do the same thing for this term as well? So what's going to be the difference? So the only difference is going to be the last term. Since if the Sn is, the n term sum, the Sn minus 1 is going to be equal to first n minus 1 term sum. What I will do, guys, I will subtract them. If I subtract them, Sn minus 1 is going to be equal, as you see, if I subtract, they will all go away, except this term. Great. Then, the only thing I know about the Sn was the limit of it, I know the limit of Sn is equal L. Let me take the limit of both sides, If I take the limit of both sides, limit of An, if the limit of Sn L, the limit of Sn minus is L, The only difference is just one term that doesn't change where it goes. That's why I look at it, the left-hand side is going to be 0. I'll look at the result. That's what I need. That was my theorem says. So limit n goes infinite, an will be 0. Perfect, right? So now, what I know this. Let me write it down again, what my theorem says. If an is convergent, if I know the convergence of my series, right, then the n term of my series will go 0. But we said that we need to know, right, the convergence of my series to be able to use this result. But if I know the convergence of the series, right, why should I use it, right? There is no such a reason, since my main question is about the convergence of the series. But from the logic, we know that, look at that, if P implies Q, right, Q prime implies P prime, right? This is the rule actually we call modus tollens. So if I use this rule from logic, guys, can I use the inverse of this theorem? Look at that. Then I can use this. If the limit of an is not equal to 0, then my series is going to be divergent. Okay? That's how I'm going to use this test. That is why they call, right, n-term test for a divergent series, right? This is also called the divergence test. So divergence test. So I'm going to be able to say if the series, right, if a given series is divergent, but I cannot say, I can't use, right, this test about the convergence. So that doesn't mean, guys, so look at that. This is the common mistakes people do. If limit of n term goes 0, what can I say about my series? Think about it for a moment. So it is inconclusive. Since the test was about, right, divergency, then I cannot say about anything about the convergence. The theorem doesn't say what will happen if the limit of n term goes 0. What the theorem says, if it is convergent, the limit goes 0. If it goes 0, I cannot say anything about the convergence of or divergence about my series, guys. Let's see some examples, right? The first example would be this one. N is equal 1, infinite, n squared minus 2, right? So, is it convergent or divergent? That's my question. So, we have two tools, right? The first one is the sequence of partial sum. But now, I learned, right, I can use the n-term test or the divergence test. I'm going to use the n-term test this time since it's not possible to use the first technique actually for this question. I'm going to skip that part. So I need to take the n-term limit. This is my n-term, guys. N-term is going to be equal n squared minus 2. And the limit of this, right, term is going to be infinite. So it is different than 0. If it is different than 0, then yes, I can say that the series, right, is divergent. Another question. Let me take a rational n-term, like this one, 3n over 7n minus 2. The question is the same. Is it convergent? Now I'm going to use the n-term test. 3n over 7n minus 2. What is the limit of this sequence, right? Look at that. the question turned into, again, the limit of sequence problem. We learned a lot of tools, right? To be able to take the limit of this one, you can either use the L'Hopital rule, since, look at that, this is the infinite over infinite, and undetermined case, that's why you can use the L'Hospital rule. So, take the derivative, which is 3 over 7, the limit of a constant is going to be equal to a constant. As you see, which is different than 0, that is why my series, right, my series is divergent, right? Okay. Another example. Another example. ln n over n, when n is equal 1 and infinite. So, is it convergent or divergent? I'm going to take the limit of n term. What is the limit of this one? Do you remember the common limits, right? Once we covered the sequences, this is the one of those limits, right? We learned the limit is equal 0. But if it is 0, right, what can I say? Is it divergent or convergent? Neither of them, right? It is inconclusive. So the test, right, doesn't give you any result. So the test will fail at this point. So it is inconclusive. So neither of them. I cannot say anything about this series. It might be convergent or divergent, depending on, right, other tasks we are going to learn later. Another example, n is equal 1 to infinite, n squared over n cubed plus 1. So is it convergent? Limit n goes infinite, n squared over n cubed plus 1. It is infinite over infinite. I can use the L'Hospital rule, right? If I use the L'Hospital, it is going to be equal to n over 3n squared. And look at this, n will go away. I will have 2 over 3n, which is equal to 0. The result, again, is going to be inconclusive. So I cannot say anything about the right convergence or divergence of the series. So, inconclusive. Okay, that's all for today. We're going to learn more tests in the upcoming class.